Understanding spectrum, forcing frequencies, and vibration units, fundamental concepts in vibration and frequency analysis. Introduction to spectrum. What is a spectrum? Types of spectra. A spectrum in vibration analysis represents the distribution of signal energy across different frequencies. It is a graphical representation that shows how vibration amplitude varies with frequency, typically obtained through a fast Fourier transform (FFT) of time-domain data. Understanding the spectrum is crucial because it helps identify specific frequency components associated with machine faults, such as imbalance, misalignment, or bearing defects. By analyzing the peaks in the spectrum, engineers can pinpoint the source of vibration and take corrective actions. The spectrum provides a clearer picture than time-domain signals because it separates complex vibrations into individual frequency components, making diagnosis more accurate and efficient. Spectra can be categorized based on the parameter being measured, such as amplitude spectrum, power spectrum, and phase spectrum. The amplitude spectrum shows the magnitude of vibration at each frequency, which is most commonly used in machinery diagnostics. Power spectrum represents the energy distribution, useful for detecting subtle changes in vibration energy. Phase spectrum indicates the phase relationship between components, aiding in advanced analysis like modal testing. Each type serves a specific purpose in vibration analysis, and selecting the right one depends on the diagnostic goal. For example, amplitude spectra are ideal for identifying imbalance or misalignment, while phase spectra help in understanding structural dynamics. Concept and sources of forcing frequencies, importance in vibration analysis. Forcing frequencies are specific frequencies at which external forces act on a machine or structure, causing vibrations. These forces often originate from rotating components such as shafts, gears, and bearings. For example, a motor running at 1,800 revolutions per minute generates a forcing frequency of 30 Hz. Other sources include gear mesh frequencies, bearing defect frequencies, and resonance conditions. Identifying forcing frequencies is essential because they often correspond to mechanical faults. When a forcing frequency coincides with a natural frequency of the system, resonance occurs, leading to amplified vibrations and potential damage. Engineers use spectral analysis to detect these frequencies and prevent failures through corrective measures. Understanding forcing frequencies is critical for diagnosing machinery health. By comparing observed spectral peaks with calculated forcing frequencies, analysts can determine whether vibrations are due to normal operation or faults. For instance, a peak at a gear mesh frequency may indicate gear wear, while harmonics of shaft speed could suggest imbalance. This knowledge enables predictive maintenance, reducing downtime and preventing catastrophic failures. Additionally, forcing frequency analysis helps in designing machines to avoid resonance by adjusting component dimensions or operating speeds. Explaining different vibration units, displacement, velocity, acceleration. Displacement measures the distance a vibrating object moves from its rest position, typically expressed in mils, thousandths of an inch, or micrometers. It is most relevant for low-frequency vibrations, such as those caused by imbalance or misalignment in rotating machinery. Displacement provides insight into the physical movement of components, which is critical for assessing clearances and mechanical integrity. For example, excessive displacement in a shaft could lead to bearing wear or seal damage. Engineers often use displacement measurements for slow-speed machines where large movements occur. Velocity indicates the speed of vibration and is expressed in inches per second, in/s, or millimeters per second, mm/s. It is widely used in industrial vibration monitoring because it correlates well with energy levels and potential damage to machinery. Velocity measurements are particularly useful for mid-frequency ranges, where most mechanical faults occur. Standards like ISO 10816 provide guidelines for acceptable velocity levels in rotating equipment. Monitoring velocity helps detect issues such as imbalance, misalignment, and looseness before they escalate into severe problems. Acceleration measures the rate of change of velocity during vibration, expressed in g, gravity, or m/s superscript 2. It is most suitable for high-frequency vibrations, such as those caused by bearing defects or gear mesh irregularities. Acceleration data is essential for detecting early-stage faults because high-frequency components often appear before significant damage occurs. By analyzing acceleration spectra, engineers can identify subtle changes in machine condition and schedule maintenance proactively. Acceleration sensors are commonly used in predictive maintenance programs for critical machinery. Comparison and usage guidelines, case study, machine analysis. Each vibration unit serves a distinct purpose in condition monitoring. Displacement is ideal for slow-speed machines, velocity for general-purpose monitoring, and acceleration for detecting high-frequency faults. Engineers often use all three units together for comprehensive analysis. For example, a turbine may require displacement monitoring for shaft movement, velocity for overall vibration severity, and acceleration for bearing health. Understanding when and how to use each unit ensures accurate diagnostics and effective maintenance planning. Consider a centrifugal pump operating at 1,800 revolutions per minute. Spectrum analysis reveals a peak at 30 Hz, corresponding to shaft speed, indicating imbalance. Velocity readings exceed ISO limits, confirming severity. Acceleration data shows harmonics, suggesting bearing wear. By integrating data from all vibration units, the maintenance team schedules corrective actions, preventing costly downtime. This case illustrates the importance of understanding spectra, forcing frequencies, and vibration units in real-world applications. Summary and key takeaways. Spectrum analysis, forcing frequency identification, and understanding vibration units are foundational to effective machinery diagnostics. By mastering these concepts, engineers can detect faults early, prevent failures, and optimize maintenance strategies. Displacement, velocity, and acceleration each provide unique insights, and their combined use ensures comprehensive monitoring. Applying these principles enhances reliability, reduces costs, and improves operational safety.